So, today I thought I should tell you how the Klebsch-Gordon coefficients are written down before we attempt this quadrupole moment using Wigner-Ricard theorem. Okay. How is Klebsch-Gordon coefficients done? So, I already explained in the Young diagram language is in the last lecture on Saturday. By the way, today I will stop the lecture at 4:45 because I think they have some recording. So, we need to leave by 4:45. Okay. So, this cross this. So, let me do only SU2 group. Now, you understand what this means is the way to see it is that the state for this can be written as J1 equal to half, M1 can be anything, that is the state which belongs to this 2-dimensional representation. M1 could be plus or minus J1, okay. And then you take a product with J2 which is half and M2. So, you are taking now a fundamental basis or a primary basis, you are taking a product of, and then this one is trivial, as I said, this is like a unit representation or a trivial representation. This you can treat it like as if it is not there, right. So, this corresponds to J equal to 0, M equal to 0, is that right? So, essentially if I want to write J equal to 1 M state, I should be able to rewrite in terms of this basis, is that right? So, I should be able to rewrite in terms of that basis. So, that is what we write, all possible values of M1 and M2, correct. J1 and J2 are fixed because the primary basis has fixed this J1 and J2. So, no J1 J2 summation. So, only the corresponding states M1 and M2 can vary between minus J2 plus J. Okay. So, M1 M2, then the notation which we are going to follow is Cj M J1 M1 semicolon J2 M2, and then you have J1 M1 product with J2 M2. Technically a tensor product, but many times they do not put the tensor product, they write by the side of it. Many books do not write it like this. Since J1 and J2 are fixed, they do not even write J1 and J2. They start with, let us look at the system with J1 and J2. Okay. So, and then this one they formally write it as M1 M2. Okay. And then there will be values here. In this particular case it is M1 half, M2 half, right. You can have M1 half, M2 minus half, M1 minus half, M2 plus half, and then M1 minus half, M2 minus half. That is the tensor product rule. When you wrote the 4 bases, you wrote it as up up, up down, down up, down down. That is what I have written here, up up, up down, down up, down down, that is a tensor product. Here you will have J equal to 1, M equal to 1, J equal to 1, M equal to 0, J equal to 1, m equal to -1, and finally you have j equal to 0, m equal to 0. These are these states. Okay. So, we need to find these elements. So, this element I would write it as j equal to 1, m equal to 1. As I said, j1 and j2 are fixed. Sorry, the m and j I am putting it as a superscript. So, let me just follow the same notation. Half semicolon j2 equal to half, m2 equal to half, okay, and so on. So, every coefficient here is the corresponding projector coefficient which helped you to determine the binary basis. Clear? Why binary? Because it is a tensor product of primary base. So, this coefficient table will be given to you. So, if suppose I give you this coefficient as 1, I think this one is 1, then you will have. So, if I give this coefficient to you, you can basically plug it in and write out the states, right. Suppose I want to write j equal to 1, m equal to 0. So, that from looking at this, j equal to 1, m equal to 0 is a linear combination of this piece and this piece with these coefficients, right. So, it becomes 1 over root 2. I am going to write a shorthand notation m1, m2 here. So, it is going to be m1 is half, m2 is minus half plus 1 over root 2, m1 is minus half, m2 is plus. So, this is the way one could read out from the Clebsch-Gordon matrix table what those coefficients are, and you can write the binary basis state corresponding to a 3-dimensional irreducible representation of SU2 in terms of fundamental objects which are spin half particles. Composite is spin 1 with these coefficients. This is the superposition of the spin states of the elementary objects which constitutes the composite object. Is this clear? Okay. So, now we let us get to the problem which we want to do. So, for completeness on the slide I have again put this thing. Okay. So, if you see the slide, I have written this formally, and then there is a procedure of determining the Clebsch-Gordon which is not pertinent to this course, but if you do it then you can appreciate this table, otherwise you can use the table. Okay. So, suppose I give you spin orbit coupling. Okay. Suppose I want to look at a system where you have an orbital angular momentum L and spin angular momentum S. S is anyway spin is half. You can combine those two, L plus, right, we can do that. What will that be? So, I can look at a situation where let us take L to be 2, okay, and S to be half. What is the Young diagram for L equal to 2? It is this. Is that right? This is for L equal to 1. Twice this number should be the number of boxes. So, how many should be there? 4 boxes. L is the orbital angular momentum, 2L should be the number of boxes representing that, because dimension of this will be, what is the dimension of this? I am doing only SU2. 2, 3, 4, 5. What is the answer? So, L equal to 2 will be 5 dimensional. So, it is 4 boxes, correct? And then you take tensor product with spin half. Spin half is always a single box, right? And then what are the possibilities you can get here? You will get 5 boxes together, and then one box can go below, three boxes that side. This can be ignored because it is like a unit representation. So, essentially it is 5 box, 5 box and then 3 box. So, what will the value of J be for this? 5 by 2, half of it, and J to be 3 by 2. So, these are the states for this, these are the states for this. This M will take values from minus 5 by 2 to plus 5 by 2. This M will take values from minus 3 by 2 to plus 3 by 2. Clear? Now, suppose I ask you to find what is J equal to 5 by 2 and M. What will you do? Again the same procedure, M1, M2. So, for this case it is L M1 and this case is half M2. M1 will take values from minus L to plus L, L is 2, so minus 2 to plus 2, and M2 is minus half and plus half. Okay. So, if I ask you to write this state, and if I give you a table like this, what I show on the screen. So, if you see the screen, I have given you column states and the row states with these coefficients. So, from there you can read out what is going to be your. So, L is 2, 2 plus half is 5 by 2 and then M. And then specific M I could take it to be, let us say if I take M to be 3 by 2, can somebody work it out and tell me what it will be by looking at this slide? J equal to 5 by 2, M equal to 3 by 2. What is that going to be? J equal to 5 by 2, M equal to 3 by 2 will be linear combinations of two states. What are the coefficients? When you substitute the coefficients, you want to see the screen again? Yeah. Just put the screen back. So, you have to see which one you have to take. Okay. Do we have to take this column or this column? The first column. And then if you look at here, it will be a linear combination of M is 3 by 2, 3 by 2 minus half is 1. So, 1 and half with the coefficient L is always 2. So, 2 plus 3 by 2 plus half, it is 2 divided by 5, root 5. Okay. So, that is one. What about the next one? So, you get, so first one you have all said, can you say the other one? 1 by root 5. Is everybody with her? 5 by 2 3 by 2 is 2 by root 5 with what is the M1 and M2? M1 is 1, M1 is 1 and M2 is half, that is 1 plus 1 by root 5, M1 is 2, M2 is minus half. Is that right? Are you all with me? Yes? This is the way to read the table and write out the states. Okay.